Okay, today we will have two types of tutorial questions. The first type is the bending shear stress, and second type will be the deflections. So we will start with the shear stress now, and we have two questions for the shear stress. This is the first one. We have a beam with I cross section and applied V, the shear force V vertically, and given the dimension of the cross section. The requirement for this question is to plot the shear stress distribution for this cross section. Fv, the shear force, is 15 kilonewton. Okay, so we need to plot the shear stress distribution over this cross section using V equal to 15 kilonewton. Okay, so now I will start doing this problem with you. So we have cross section I. And the dimension of this cross section is 12 millimeter, 60 millimeter, and 12 millimeter. The dimension in the horizontal direction is 20 millimeter, 80 millimeter, and 20 millimeter. Okay, and the applied shear force V is vertically, and given V equal to 15 kilonewton. Okay, and the requirement to plot shear stress. Distribution. Okay. The first thing we need to know now is what is shear stress, what is the formula for shear stress. Shear stress, we indicate shear stress with tau. Tau is the shear stress at any point. The shear stress is equal to V is the shear force multiplied by Q is the moment of area divided by I, inertia, multiplied by T, which is the thickness. Okay, so V is the shear force applied to the section. Q is the moment of area at this point. I is the inertia of the section. We know how to calculate I from the previous week. Inertia, which is I x dash. T is the thickness or the width of the section, thickness at this point. Okay, so this is the formula for shear stress at any point. Tau equal to V Q divided by I T. Okay, and we will know now how to find everything in this equation. Okay, first of all, we will start with I, which is the inertia, I x dash. How we can calculate I x dash for this section? Last week to find ix dash, we need to find y bar or the centroid location, y bar and x bar. But here, because this section is symmetric, so y, this axis is symmetry, axis of symmetry. So this is y dash axis, and also x is a symmetry axis. So this is x dash axis, and the centroid will be here at the middle of the section. This is the centroid or CG. Okay, so we don't need to calculate y bar because we already know where is the centroid. So we directly will calculate ix dash. To calculate ix dash, last week we divide the or subdivide the section to regular section or regular shapes. So we have number one is this one, rectangular. Number two is similar, rectangular here. And number three is rectangular here. So for the first rectangular, the width is 120 millimeter, and the height or this is the length or width, and this is the other dimension is 12. So I will start with this one. The centroid of this area 1 is here. So the centroid of area 1 is not coincide with the centroid of the whole section. So the inertia for area 1 will be the parallel to x, which is 120, multiplied by the normal to x, which is 12 to the power 3, divided by 12, plus the area 120 multiplied by 12 multiplied by the distance from centroid of area 1 to centroid of the whole section, this distance will be y1. The whole height is 12 and 12 and 60 is 48, 84. So the half will be 42. Okay, and the distance from the centroid of area 1 to the top of the whole section is 6, because this is 12, so the half is 6. So y1 will be 42 minus 6, which is 36 to the power 2. This is y1. So this is the inertia for area 1. And because area 1 and 2 are similar, so we will multiply this we will multiply by 2, because area 1 and 2 are similar. Plus, for area 3, the dimension is, the width is 80 and the height is 60. So area 3 parallel to x is 80, multiplied by the normal to x, which is 60 to the power 3, divided by 12. And the centroid of area 3 is here, and the centroid of the whole area is the same point, so they are coincide. So the term area multiplied by y square is not applicable here, so 0. So the final result for inertia ix dash will be 5.207 multiplied by 10 to the power 6 millimeter to the power 4. Okay, and this calculation, we have done this before in the normal stresses. So now we know I and we know V, so we still need to know Q and T. Okay, so the next step is to find Q and T. So again, tau equal to V Q I T. And we already know V given 15 kilonewton. I from the calculation Ix dash equal to 5.207 divided by 10 to the power 6 millimeter to the power 4, and this is the cross section again. And we know that the centroid is here. This is X dash, Y dash, and this is our centroid. The dimension again is 12, 8, 60, and 12. And here 80, 20, 20. Okay. So next step is, after knowing V and I, we need to know Q and T. Okay. I will start with T. T is the thickness at the point we need to calculate the stress. Okay, if we need to calculate the stress at this point, something here at the middle, if this is our point of stress, so what is the width at this point? The width T is this width, the width of section. So this is T1. So this T1 maybe, if we have a look on the dimension, will be 120. Okay, if we need to calculate the stress at some point here, point 2, so the width will be at this section will be T2 equal to 80. Okay, so T is the thickness of section at point of stress. Okay, the last thing we need to know is Q. Q is the moment of area at point of stress around the CG. Okay, what this mean? This mean if this is the area, if this our cut or our section, we need to calculate the stress as, so this is the point of stress, and this is the centroid of the whole section here, CG. So Q will be equal to the area, this area, the hatched area, this area, if we can call it as TB or T. So Q will be the area multiplied by the distance from the centroid. This is the centroid of the section, of the area, from the CG for the whole section. So this will be Y. So Q will be area multiplied by distance Y. Y is the distance from the centroid of the area to the centroid of the whole section. Okay. So the unit of Q, if area millimeter square and Y is millimeter, So Q will be millimeter to the power 3. Okay, this is Q. So now we know to calculate tau, the shear stress, we need the shear force V. Q is the moment of area at point around the CG. I is the inertia. T is the thickness. Okay, so now we can apply this to our problem now. I will save this one. If we return back to our problem here,
You can select the cut tool to be faster.
okay, this one.
Yeah. You select, yep, and then Ctrl X.
Okay, thank you, thank you. Okay, so I will also need to. Okay, so now we will apply this formula to our section. So if we need to calculate the shear stress at any point for this section, what we will do, we will apply this formula. But here the requirement is the shear. Notice the stress at only one point. We need the shear stress at, or the shear stress distribution. The shear stress distribution mean the shear stress for the whole section or the whole cross section. Okay. So if this is our section, so we need to draw a datum here. The datum is always parallel to the shear force. If you remember, the applied shear force V was vertical, so our datum will be vertical, and we will have some cut to draw to indicate the shear stress or to help us to draw the shear stress. These cuts will be at the beginning or the start of the section 1, and before and after any change in shape, because we have here the width was 120 and at this point will become 80, so we have cut 2 and we have here cut 3. Cut 2 and 3 at same point, but before and after the change in thickness. Okay, and we need cut at the centroid of the whole section, so this cut 4, and again here we will have cut 5, and here cut 6, and here cut 7. So for this cross section, to draw the shear stress distribution, we need 7 cuts. Using these 7 cuts, we will have like guidelines, these guidelines to help us to plot the shear stress. Okay. If we calculate the shear stress, we will have a value of stress at 1, then value stress at 2, then value stress at 3, then value stress at 4. Then we can connect them using curved line and straight line, something like this, and then this value here, and we can connect, then a value here, then the value here will be 0. So we need value at 1, value at 2, value at 3, value at 4, value at 5, value at 6, value at 7, and finally this plot is the shear stress distribution. Okay, this is what we will do. This is indication of what we will do now. Okay, so we need to for the plot, we need the shear stress at many points, not one point only. So we need at least here 7 points. But if you have a look on this cross section, x dash is axis of symmetry. So section 1 or cut 1 is similar to 7. So 1 similar to 7, 2 similar to 6, and 3 similar to 5. Sorry, 5. And we have 4. So we don't need to calculate at 7 and 6 and 5. So we have only to calculate at 4 cuts. Okay. So I will start now to calculate the shear stress at 1. Tau 1. Tau 1 is the shear stress at 1. The shear stress formula is V. V is equal to 15 kilonewton. And for your information, we have in this course, it's better to use the units of Newton and millimeter to make it easier for you. So if we have kilonewton force, how to convert it to Newton? So we need to multiply by 1000 or 10 to the power 3. So 15, I will multiply it by 10 to the power 3 to be in Newton. Then I, we just got I, 5.207 multiplied by 10 to the power 6. Okay. And T, sorry. What is T? T is the thickness of the cross section at this point. So if we are at 1, this is cut 1 here. So the thickness of 1, this is the thickness of cut 1. So it will be 120. So T will be 120. So the last thing we need to know is Q. Q1. So I will put Q1 here. How can we find Q1? Q1 generally is the area multiplied by Y. If we are at cut 1, here is cut 1. This cut 1. If we make cut, so we have, this is the area above 1 and the whole section is below 1. So what is the area at 1? It's better we can use the area above or below the cut. So the area above the cut is 0 because this is the beginning of the section, so no area before it. So Q1 is equal to 0. So if Q1 is 0, what is the value of tau 1? Tau 1 will be 0. So you need to keep in mind that the shear stress at the beginning or end of any cross section will be 0. Okay. The second point or the second cut, tau 2. Tau 2 is similar formula, 15, because 15 is the applied load similar, like constant for the whole section. So 15 multiplied by 10 to the power 3. This is the applied force or the applied shear force. The inertia also for the whole section is similar. So 5.207 multiplied by 10 to the power 6. Okay. Here we need Q and T. T, what is T here? T, again, if this is our cut 2, so this is T. Is there any difference between T at 1 and T at 2? They are similar, so T1 equal to T2 equal to 120. Okay, so now we need to know Q2. How can we find Q2? Q2 is area at 2 or area 2 multiplied by Y2. What is area 2? Again, if this cut 2 here, so this is the area above cut 2, the hatched area. So area 2 will be 120 multiplied by 12 multiplied by Y2. What is Y2? Y2 is the distance from the centroid of area 2 to the centroid of the whole section. This is Y2. How can we find Y2? We just calculate Y2 in the previous step, because we know that this is 42 and the distance from the centroid to the top surface is 6. So Y2 will be 36. So finally we can find Q2. Okay, Q2 will be just give you the answer of this one. It's 51,840 millimeter to the power 3. Okay, so now we know Q2 and we can substitute with this value here and get tau 2. Tau 2 was 1.24 MPa. So this is the value of tau 2. Okay, so we find the value of tau 1 and tau 2, and now we can shift to tau 3. How can we find tau 3? Similar equation. Tau 3 will be 15 multiplied by 10 to the power 3 divided by I. I is 5.207 multiplied by 10 to the power 6. Then we need to find T and Q. What is T at 3? If we are at 3, so this is cut 3 here. Cut 3 here. So if you have a look here, this is T at 3. T at 3 is 80 millimeter. Okay. And this will be the difference between tau 2 and tau 3, because tau 2 and tau 3 are at same point. But because there is a sudden change in the thickness, so we need to calculate at this point. So we have cut 2 and cut 3. Cut 2 and cut 3 will be similar except for T. T before the sudden change is 120, and after the sudden change is 80. Okay. Then we return back to Q. What is Q here at 3? Q is the area before cut 3 multiplied by Y. And because Q and because 2 and 3 are similar or at same point, so Q2 equal to Q3. So you can keep in mind at any point, if we are at same point, Q is constant, because Q depend on the area and the distance. So Q2 and Q3 are similar. So we don't have to repeat the calculation again, and we will put here Q3 is 151,840. So this gives us tau 2 equal to tau 3, sorry, 1.87 MPa. Okay. So tau 3 is 1.87, tau 2 is 1.24. Why tau 3 is larger than tau 2? Because T3 is smaller than T2. T2. Okay, because at any point the only thing will be different in the equation is T, because we are at same level or same cut. Okay, so we now get tau 1, tau 2, tau 3, and the last section we need to find is tau 4. How can we find tau 4? using same equation, we will find tau 4. So tau 4 will be 15 multiplied by 10 to the power 3 divided by I 5207 multiplied by 10 to the power 3 multiplied by T and multiplied by Q. What is T here? Here, this is cut 4. This is cut 4. So what is T at 4? T at 4 is this width or this thickness. So T at 4 is 80. So T at 4 is 80 millimeter. And what is Q at 4? Q at 4 will be the moment of area of this whole part. Okay. This whole part will be Q4. So Q4 will be summation of area multiplied by Y above section 4. What is the area above section 4? I can do it for you in another slide. So now we have this section. And assuming this is cut 4. So we need to calculate tau 4. We have 15 multiplied by 10 to the power 3 divided by I 5207 multiplied by 10 to the power 6, and we know that T here is 80, and we need to find Q4. So Q4 is equal to summation area above 4 multiplied by Y. So equal to, what is the area above 4? We have two areas. This is area 1 and this area 2. And we know that this is the centroid of the whole section, because this X dash, this Y dash, and here is the centroid. The centroid for area 1 is here. The centroid of area 2 will be here. So this is area 1, so this will be Y1. And this area 2, this will be Y2. So Q4 will be area 1. This was 12 and this was 30. And the width here was 120 and the width here is 80. Okay, so Q1 will be area 1 120 multiplied by 12. This is the area multiplied by Y. What is Y? Y, we just said before, this the whole height from the centroid to the top level is 42, and from here to the centroid is 6. So Y1 is 36 plus area 2. Area 2 will be 80, the width multiplied by the height, which is 30, multiplied by Y2. What is Y2? If this is 30, so Y2 should be 15 millimeter. So 15 millimeter. And we can now find Q2. So Q4, sorry, will be 120 87 84 0 millimeter to the power 3. So using Q4, we can now find that tau 4 equal to 3.16 MPa. So we now know tau 1, 0, tau 2, 1.24, tau 3, 1.87, tau 4, which will be tau maximum, equal to 3.16 MPa. If you have a look here, the maximum shear stress we find is 3.16 at cut 4. Why at cut 4 here is the maximum shear stress? Because you should keep in mind that the maximum shear stress will be always at the centroid. So the section at the centroid or the cut at the centroid give you the maximum shear stress. Why give you the maximum shear stress? Because at the centroid Q is Q maximum. So because Q maximum is controlling tau, Q is controlling tau. So if we have Q max, this give us tau max. So for another problem, if he asked you to find the maximum shear stress, we don't have to calculate at 1 and 2 and 3 and 4. We will only calculate at 4 because section 4 is at the centroid and will give us the maximum shear stress. Okay. So now if we want to finalize this problem, the requirement was to plot the shear stress distribution. Now we got the value of the shear stress. So the final step is to draw the shear stress distribution. This is our neutral axis, or this our y bar, y dash and x dash. And we said before we will have datum. This datum is parallel to the shear force V. So we have shear force and we have cut 1, cut 2, cut 3, cut 4, and these cuts are similar because we have symmetric line, and we will have this guidelines here. And now we can put the values we got. So at 1, the shear stress was 0. At 2, the shear stress was 1.24. At 3, the shear stress was 1.87. At 4, the shear stress was 3.16. And now we can connect these values together. From 1 to 2, we will connect with parabola. From 2 to 3, because they are on same line, so we will connect with a straight line. From 3 to 4, we will connect again with a parabola. And the values here, because it is symmetric, so this is 1.87. And here will be 1.24. And here 0. And we will connect again with parabola here. And we connect here from 2 to 3 with a straight line, and here with a parabola. So this is tau distribution or shear stress distribution. Okay.
We use the straight line to connect those points.
Which points?
Yeah, like those 7 points. Like, can we use straight lines?
No. Again, I will tell you again. Generally, we connect the points with a second degree parabola because the relation between the depth and the shear stress is from the second degree, not first degree. So we cannot connect with a line, a straight line. Okay. But here, because we are at same height, I tell you before why we have two cuts at 3 and 2? Because we have two thickness. So if we have two thickness, we will have a drop in the shear stress. Okay. But because we are in same line, so we connect with a straight line because we don't have to connect with a parabola here or a parabola here. Okay. So if our cut at the same level of the section, so we connect with a straight line. But if we transfer from one point to another point here at different height, like 1 and 2, 1 and 2 are different height at different heights. So we connect with a parabola. Again, here from 3 to 4, we have different height of the section. So we connect with a parabola. Okay. So we connect only with a straight line at these 2 points because we have just a sudden change in the shape. So we have to connect them with a straight line. Okay. You get it?
Yeah, I got it.
Okay. Do you have any other questions for this problem?
Yeah, can you mute that guy, Goyo? Because like his mic is so noisy.
So
Okay.
red.
Okay. We have now finished the first problem. So we'll shift to the second one now. For the second problem, this is our second problem. It is similar shear stress problem, but we have a small idea before getting into the shear stress. Here, given a beam, a simple beam with two loads, concentrated load 20 and uniform load, and given the cross section of the beam is T section, and the requirement is to find the maximum shear stress. So the first step, we don't have the shear force, so we have to get the shear force from the beam. Then using this shear force, we will apply this shear force to the section to get the shear stress. Okay, this is the idea in this one. So I will now solve this one with you. For this beam, we have simple beam, and we have a concentrated load 20 kilonewton here, and we have uniform load 8 kilonewton per meter, and the dimension or the spans here 3 meter and 2 meter, 2 meter. This is point A, and this is point B, and this is point C. Okay, so from this beam we will try to find the maximum shear force, V max. How to find the maximum shear force? To find the maximum shear force, we need to draw the shear force diagram for this beam. So this is like a revision for what we have done in the first 3 or 4 weeks. Okay, to draw the shear force diagram here, we need to first calculate the reaction or find the reaction. We have 3 reactions, XA, YA, and YC, sorry. So if we apply the equations, summation fx equal to 0, this gives us XA should be 0. Summation moment at A equal to 0. If we apply the moment here equal to 0 at A, so we need to concentrate the uniform load first here, 8 multiplied by 3, so 24. So what cause moment at A? YC, so 24 and 20. So YC multiplied by 7 minus 24. What is the distance of 24? 24 is at the middle of this distance, so 1.5. So from A to 24 will be 5.5 meter minus 20 multiplied by 2. All of this should be 0. This gives us YC equal to 24.57 kilonewton. So this is the reaction at C. If we apply summation Fy equal to 0, this gives us Ya minus 20 minus 24 plus the reaction Yc 24.57 should be 0. So we will get Ya equal to 19.43 kilonewton. Okay, so the reaction at C 24.5, the reaction at A is 19.4. So now we can return to our beam to draw the shear force diagram. If you remember, we have some cuts, cut at the start of the beam, cut before and after the concentrated load, cut at the beginning of the informal load, and cut at the end of the beam. So we have 5 cuts here. Okay, and we need to calculate the shear force at this 5 cuts. And this our guidelines. This our guidelines, and this our datum to draw the shear force diagram. So we will draw the shear force diagram over this datum. What is causing shear at section 1? If we calculate from this direction, so we have Ya 19.43 kilonewton. From cut 1 to cut 2, we don't have any applied load, so straight line parallel to the datum 19.343. Okay. From 2 to 3, what we have from 2 to 3, we have 20 kilonewton downward. So from 19 to 20, so we will have only small value here, 0.57 kilonewton. From cut 3 to 4, we don't have any loads, so straight line parallel to the datum with the same value, 0.57. From cut 4 to cut 5, what we have from 4 to 5, we have a uniform load for 24. So from 0.57 with the for 24, so we will reach here 24.57. And after cut 5, we will have the reaction YC, which is the same value here. So this value will reach us to 0 again. So we start from 0 and end at 0. And the shear stress here is positive and here is negative because the sign convention for shear force above the datum positive, below the datum is negative. From this shear force diagram, what is the maximum shear force? You have to find the maximum value of the shear here. So the maximum value is this value. The maximum value is 24.57. So from all this calculation, finally you find V maximum equal to 24.57 kilonewton. This was given directly in the last problem we solved, but here you have to do some calculation to find Vmax. This is another idea of the shear stress. Okay, so now we finished the shear force calculation, and now we can shift to the second step. The second step is to find the shear stress, the maximum shear stress. Given to us the shape of the section, T section, The dimension is 100, the width here, and here 20, here 20, and 100. Okay. So this is the dimension of the section. And now we need to calculate tau max. Tau max is equal to V maximum multiplied by Q maximum divided by I multiplied by T. This is the general value or the general formula for shear stress. Now we only know from the previous calculation V max 24.57 kilonewton. So we still need to find I and T and Q max. Okay. How to find I? We need to find I x dash, which is the inertia of this section. How can we find I x dash? To find I x dash, we need to know where is the location of centroid y bar, because we all here only y is a symmetric or axis of symmetry. This is y dash, but x is not in the middle, so we need to find x dash. How can we find x dash? To find x dash, we will assume we have a virtual axis here or a guide axis here x, and the distance from x dash to x will be y bar. So first step to find y bar. If you remember from last week, y bar was summation area y, area multiplied by y divided by the summation of areas. Okay, so here we need to divide the section to two regular section, 1 and 2. This is a centroid of 1 and this is a centroid of 2, and this is the centroid of the whole section. Okay, so for y bar will be area 1 100 multiplied by 20. This is area 1 multiplied by y. What is y? Y is the distance from centroid of area 1 to, sorry, y is the area from the centroid of area 1 to the virtual axis x. This is y1 for the calculation of the centroid. Okay, so this is y1. What is y1 here? The distance from the top to the centroid is 10, and the total distance here is 120. So y1 will be 110 plus area 2. Area 2 is 100 again multiplied by 20 multiplied by y2. What is y2 here? y2 is the distance from the centroid of area 2 to x. So if this 100, so half will be 50. So this will be 50 divided by the summation of area. Summation of area is this area plus this area. So 100 multiplied by 20 multiplied by 2, because the two areas are similar. So y bar will be 80 millimeter. This is y bar, 80 millimeter from bottom. So this y bar will be 80 millimeter. And if you do this calculation from the top, so this will be 40 millimeter. Okay, y bar depend on what is the axis you assumed. X, maybe you assume x at the bottom level or at the top level. Anyway, this y bar is related to top or bottom level. So if from bottom level here, so 80 from bottom will be 40 from top, and and so on. Okay. So now we get y bar. The second step is to find ix dash. How can we find ix dash, the inertia for the section? Ix dash will be the inertia for area 1 plus the inertia of area 2. For area 1, the inertia will be the parallel to x, 100, multiplied by the normal to x is 20 to the power 3 divided by 12 plus area, which is 100 multiplied by 20 multiplied by y square. What is y here? Y here is the distance from the centroid of area 1 to the centroid of the whole section. This is y1. So if this 40 and this 10, so this will be 30 millimeter. So this will be 30 millimeter. Plus, so this is the inertia for area 1. The inertia of area 2 will be the parallel to x, 20, multiplied to the normal to x, 100 cubic, divided by 12. Plus, the area will be 100 multiplied by 20 multiplied by the distance y square. What is y square here? Y square here is the distance from the centroid of area 2 to the centroid of the whole section. This 80 from y bar is 80 and this 50, so this will be also 30 millimeter. So this will be 30 millimeter. And now we can finally get ix dash will be 5.33 multiplied by 10 to the power 6 millimeter to the power 4. This is ix dash. So now we know ix dash, phi, and we still need q max and t. Okay, so we can go now to the next step. We know V max or V 24.57 kilonewton. Ix dash equal to 5.33 multiplied by 10 to the power 6 millimeter to the power 4. And this is our cross section. And we know that the centroid here x dash y dash, and this distance is 40, 80, and this distance was 20, 100, and this is 20, and this is the centroid. Okay, so now we need to find tau max again. V multiplied by Q, I, and T. And we said to find tau max, we need Q max. Where is Q max? Where is Q max? Q max and tau max is at the centroid. So this is where tau max. This is cut. Tau max will be at the centroid and will be here. So to find Q max, we will have these two areas, area 1 and area 2. Okay, so we need to find Q max, which will be the moment of area for this yellow area, this area multiplied by the distance from the centroid of this area to the centroid of the whole section. Okay, so Q max will be, the yellow area is 100 multiplied by 20 multiplied by the distance. What is this distance? If this 40 and this was 10, so this distance will be 30 plus area 2. What is area 2? Area 2 is this small area. Okay, so area 2 will be, if this 40 and this 20, so the height of area 2 is 20. So area 2 will be 20 multiplied by 20 multiplied by the distance from the centroid. So where is the centroid of area 2? The centroid of area 2 is here at the middle. So if this 20, this will be 10. So area 2, 20 by 20 multiplied by y, which is 10. This gives us Q max. I'm going to find Q max for you. Q max will be 64,000 millimeter to the power 3. So we know now V, Q, and I, we still T. What is T? T will be the width of the section here, which is 20. So T will be 20 millimeter. So finally, if we substitute in the formula of tau, tau max will be 24.57 multiplied by 10 to the power 3 to convert to Newton, multiplied by Q. Q is 64,000 millimeter to the power 3 divided by I, 5.33 multiplied by 10 to the power 6 multiplied by T. T is 20 millimeter. All this calculation give us tau max 14.7 MBA. Okay. So finally, we get that shear stress, the maximum shear stress for this cross section, and you should know that the maximum shear is at the centroid of the whole section. This is the idea to find the tau, the maximum tau. Okay. Do you have any question for this problem? Okay, all good with this one. So now we finished the shear stress problem, and we will now shift to the deflection problem. Okay, we have two questions for beam deflection. The first one here is a simple beam, and the second one is cantilever. Okay, so now I will start with this problem, the deflection problem. Okay, but before I start, I will give you some basic formulas to keep in mind, because we will need them in our calculation. Okay, we have 4 cases of beam deflection, 4 basic cases. The first one is simple beam with cantilever. Simple beam with applied load is concentrated load. So if we have simple beam with span L, simple beam mean we have hinge or roller to the left and hinge or roller to the right. So if we have simple beam with span L and we have applied load B in the middle, B. Okay, the deflection will be something like this. After applying the load, the beam will deflect. The maximum deflection will be at the middle, delta max or delta. Okay, So we need to find the value of the deflection delta. For this case, delta will be B, the load, multiplied by L to the power 3 divided by 48 EI. Okay, where L, what is L? Or what is B first? B is the load, concentrated load, B. L is the span of the beam, or the length of the beam. 48 is constant for this relation, constant. E, what is E and what is I? E is, you know, Young's modulus, is a material property. So yeah, this is Young's modulus. I is the inertia of the beam, Ix dash. So for any simple beam with concentrated load in the middle, the maximum deflection will be in the middle, and the value of this deflection will be BL to the power 3 divided by 48 EI. Okay. The second step, the second case, is also simple beam, but with uniform load instead of concentrated load. If we have uniform load W and the span is L, the deflection or the deflected shape for this beam is similar to that of the concentrated load, and the maximum value will also be in the middle, delta. This is the deflection value. Delta here will be 5 W L to the power 4 divided by 384 EI. Okay. Here W is the uniform load, uniform distributed load. L is the span of the beam. 5 divided by 384 is constant for this relation or this formula. E, again, Young modulus. I is the inertia of the beam, Ix dash. Okay. So you need to keep in mind these two formulas for simple beam with concentrated load in the middle and uniform load. If we have a look on these two formulas, you will notice that for concentrated force, L is to the power 3. So if you have any concentrated force or concentrated load, L will be to the power 3. But here, for uniform load, L will be to the power 4. This is a basic difference between the two formulas, and you have to keep in mind. 3 if you have concentrated load, 4 if you have uniform load. Okay. The third case we have is if we have cantilever. Cantilever beam means beam fixed from one end and free from the other end. If we have fixed free beam with span L and we have concentrated load B at the free edge. Okay. The deflection or the deflected shape here will be something like this. The maximum deflection delta will be at the free edge because it is not allowed, it is not supported by anything, so it will drop. Okay. Delta here will be B L to the power 3 divided by 3 E I. Okay, again, B is the load, L is the span, 3 is the constant for this relation, E Young modulus, I is the inertia. And if we notice here, L is to the power 3 because we have a concentrated load. The first case we have also cantilever, but cantilever with a uniform load W. If we have a beam or a cantilever beam with uniform load W and span L, the deflection or the deflected shape here will be like the previous case. Delta here is same shape to here, but only the value is different. Delta here will be W L to the power 4 divided by 8 EI. Okay. W is the uniform load, uniform distributed load. L is the span. 8 is the constant of this formula. E Young modulus. I is the inertia. Okay. And if we notice again here, if we have uniform load, so L to the power 4, not to the power 3. Okay. So these 4 cases is the main cases we need to know, basic cases, because we have a lot of cases. You can find them in any textbook. If you have a load not in the middle, or if you have any shape of beams, we have different cases. But for our course or our scope, we have to focus only on these 4. Okay. So now we finish the basic formulas for beam deflection, and I will return back to the beam, to the questions. Okay, this is our first question today for beam deflection. We have here simple beam AAC with 2 loads. B is concentrated load and 5 kilonewton per meter is uniform load, and we need to find the deflection at point B. This is the maximum deflection. Okay, if E is 200,000 MPa and given the cross section I. Okay, so I will now start solving this with you. For our first beam, we have simple beam. For this beam, we have 2 loads, 20 kilonewton and 5 kilonewton per meter, and the distance or the span here is 6 meter, 3 meter, and 3 meter. And given the inertia or the section is I beam. This I beam 100 millimeter, 10, and this 10, 110. Okay, so now we need to find the maximum deflection at point B. To find the deflection at B, delta B will be superimposition of the 2 cases we have for simple beam, because we will have deflection from the concentrated load and we will have deflection from the uniform load. So delta B will be B L to the power 3 divided by 48 EI. This for the concentrated load, plus for the uniform load 5 W L to the power 4 divided by 384 EI. This is for the uniform load. So the final deflection will be superimposition of the 2 terms. Okay. If we have a look on what we know in these formulas, we know B given the load, given the span, given E, because given E in the question, E is equal to 200,000 MBA. So given E, the only thing we need to know before starting calculation is I. Also here we know W, L, and E, and we still need to know I. Okay, that's why he gives you the cross-section dimension and cross-section shape. Okay, to find Ix dash, how can we find Ix dash for this beam? Do we need to find the centroid location? No, because we already know that this is symmetric section in about X and about Y. So the centroid is somewhere here in the middle of the section. This is our centroid here. And we will divide this section to 3 parts or 3 areas, area 1, area 2, and area 3. The centroid of area 1 is here, the centroid of area 2, 3 is here, the centroid of area 2 is similar to area 1 is here. Okay, so Ix1, Ix dash, sorry, will be summation of inertia for the whole section. So for Ix1, the parallel to X is 100 multiplied by the normal to X, which is 10 to the power 3 divided by 12, plus the area 100 multiplied by 10, this is the area, multiplied by the distance y. What is y here? Y is the distance from the centroid of area 1 to the centroid of the whole section. Okay, this, the total height is 120, so half is 60, and this is half of 10, so this is 5. So y1 will be 55. So 55 multiplied by 55 to the power 2, and because we have area 1 and area 2 are similar, so we'll multiply this by 2 plus ix dash for area 3 will be the parallel to x, which is 10, multiplied by the normal to x, which is 100 to the power 3 divided by 12. And because the centroid of area 3 coincide with the centroid of the whole section, so the second term is not applicable here. So Ix dash will be 6.9 multiplied by 10 to the power 6 millimeter to the power 4. Okay, and now we know all the parameters, so we can apply in the deflection equation. So deflection at B will be B. What is B? Given B is 20, and we said before the dimension better to be in Newton and millimeter, so we'll multiply it by 10 to the power 3 multiplied by L. Given L 6 meter, to be millimeter we will multiply by 1000, so will be 6,000 millimeters. So 10 to the power 3, and then L is 6,000 to the power 3 divided by 48 multiplied by E, 200,000 multiplied by I, just calculated, 6.9 multiplied by 10 to the power 6. So this is the deflection from the concentrated load. Plus, for the uniform load, we know 5 multiplied by W. Here, if we have W is the load equal to 5 kilonewton per meter. How can we convert this to Newton per millimeter? To convert kilonewton to Newton, we will multiply by 1000. And to convert millimeter to convert meter to millimeter, we will multiply down the dash, below the dash by 1000. So 5, the final result will be 5 Newton per millimeter. This means that kilonewton per millimeter is equivalent to Newton per millimeter. So 5 is a constant multiplied by W, which is 5 as well, multiplied by deflection is a span 6,000 millimeter to the power 4 divided by 384 multiplied by E, same E and same I. This for the uniform load. Okay, this gives us that the deflection for the first term was 65 millimeter, plus the deflection from the uniform load was 61 millimeter. This gives us the final deflection was 126 millimeter. So the deflection at B for the two loads, uniform and concentrated load, will be 126 millimeter. Okay. So this is the deflection for beam 1. If we return back to the problem we have, the second problem is quite similar to the first one, except for the beam shape. This is a cantilever beam instead of simple beam, but same loads, 5 kilonewton per meter uniform load, 20 kilonewton concentrated load, and the cross section is similar. Okay, so now we will start this one. We have a cantilever beam. The span is 3 meter, and we have concentrated load B here is 20 kilonewton, and we have a uniform load here is 5 kilonewton per meter, and the shape, the cross section shape is similar, IB. If the cross section is similar, this means one thing only. This means that IX dash, you don't have to calculate again. IX dash is 6.9 multiplied by 10 to the power 6 millimeter to the power 4. Okay, so if this be AB, the maximum deflection delta B, or the required deflection delta B, will be superimposition of two values. For concentrated load, we know that B L to the power 3 divided by 3 EI is the value of deflection for concentrated load. Plus for uniform load, B L, sorry, W L to the power 4 divided by 8 EI. This for concentrated load B, and this for uniform load W. Here delta B, the deflection at B will be, B is given 20 multiplied by 10 to the power 3 multiplied by L. L is 3000 millimeter to the power 3 divided by 3. E is 200,000. I, we knew I from the first problem, so I is 6.9 multiplied by 10 to the power 6 plus, this is for concentrated load, plus for uniform load, W is 5 kilonewton per meter, and similarly will be Newton per millimeter, multiplied by L, 3000 to the power 4 divided by 8 multiplied by similar E and similar I, and this is the deflection for uniform load. So delta B finally will be For the concentrated load, 130 millimeter, and for the uniform load is 36 millimeter. So the final deflection will be 166 millimeter. So the deflection at B for this case will be 166 millimeter. Okay. So this is a deflection calculation we need to do today. And do you have any questions for this calculations?